Go ahead and get started. One brief announcement. There will be an extra credit assigned, which you can start working on. A second problem, and that will help improve your second exam score for those of you that have high anxiety and feel like you don't do that well. So there'll be a chance to give a improvement. The due date will be after April 15th, however. So there's still some time. In fact, I would probably say the nearest class period, April 15th, will probably be when I will do it. Again, a lot of things, several things coming up. First chapter 1 homework due tomorrow night. Second one due Tuesday night, exam on Thursday. And the Thursday exam will be chapter 40, 41, and the parts of 39 that we did not cover. In other words, only the relativistic kinematics will be on this exam for the relativity portion of the test. Okay? So I will get chapter 42 homework started fairly soon. I don't have them posted yet. So today I'm planning on finishing 41, and then we'll be ready for chapter 42 on Tuesday. Okay? So that's a little bit of what we have. Okay, so I think what I'll do is I'll start with a brief review of what we discussed last time in terms of a particle in a finite well. Particle in finite well. And we talked about, we always draw our potential energy diagram and our total energy levels that are consistent with a quantum mechanical system. And for that, we draw, this axis is the axis in x, spatial position x. This is either the u or the energy axis, u being potential. So generally what we do first is we draw the potential energy curve for the problem that we're trying to solve. And the problem that we were solving the other day was one in which there's a potential height barrier of U0. We were looking for solutions for particles trapped in the well. They have energy levels E1, E2, and in addition they have wave functions associated with them. For the ground state energy, they look very much like the infinite well, only they don't really come all the way down to zero. And we said there was a probability that it could go into, this is the classically forbidden region, because if this energy E is 1/2 mv squared, of course this is energy E2, 1/2 mv2 squared. And this is the energy E1, and there might be more energy levels, E3, E4, etc. But this obviously, in the case where the potential energy is 0, tells us that this height, well, the total energy minus the potential is always the kinetic energy. So this height is always the kinetic. There's a wave function associated with these different energy levels. We talked about last time. There was psi1 of x, which is what we call the ground state energy level. There is the next one up is the one that comes up like this. And let's see, this one goes up. This is a full wavelength. So something like this, and then there will be exponential fall off in this region right here. Now, this is what we said was this region is the classically forbidden region, because in a classical system, forbidden region, right? In a classical system, the total energy E must be greater than the potential energy, because E is equal to kinetic energy plus potential energy. So the total energy must be greater than potential. Here, the total energy E is less than the potential, right? So this is a region that we would normally call negative kinetic energy, which of course is not possible, therefore it's forbidden. But we also said that it's possible in certain cases where the particle can go into classically forbidden regions, and there will be the amount of which energy conservation is violated is given by this quantity, which we call delta E. And that delta E, a particle can be in that region for a given amount of time equal to h bar divided by delta E. In other words, energy conservation can be violated by an amount. This is the amount of energy conservation violation. Can somebody close the doors up there? Appreciate that, right? Thank you. Thank you. That one too. Great, thanks. Appreciate it. Energy conservation violation, and it can occur as long as it doesn't spend more than an amount of time delta T in these forbidden regions, which means that it's got to get back, right? In other words, it can go over here, but it can only spend a finite amount of time over there, and then it's got to get back into the classical allowed region. So this is the classical allowed region for a particle in a box. And it's clear from the way this is drawn that if the probability is going down as you go further and further out, that means that the particle is less likely to be found out here than it is here, and therefore it will spend, the particles will return back to their region before they get this far out, this far out, or this far out. So it's an exponential decay function, and this exponential decay has a form that we said last time, which was, if I labeled these regions 1, 2, and 3, 3 being the one to the right of the potential well, then psi 3 of x was equal to, in our notation, a constant times e to the minus gx, and g was equal to the square root of 2m times the potential energy minus the total energy divided by h bar. Okay? And this is how we use the quantum expression to calculate what is the probability of finding it in a region between x and x plus dx. So this would be d squared, and if I want to find the probability of it being located, let's say, between a distance a from the origin and a distance 2a from the origin, then this probability that would actually be the integral of d squared times e to the minus 2gx times dx. And I can do the integral and I can evaluate this, but the idea is this is a probability function, right? And the amplitude squared, or the wave function squared, tells me the probability of it being found at a certain location. Okay? So that's just sort of a brief review of what we had last time. Yeah, I think that's it. Now there are the reason there are a couple areas where this potential well problem is important. It's actually going to be important for some of your applications when we come to the chapter on semiconductors, conductors, and semiconductors and conductors, I should say. We are going to model a block of aluminum, say, for example, as having electrons that are populated throughout here, and I can consider that these electrons are trapped within the boundaries of the block so that the electrons cannot get out. And in this particular case, we will have an infinitely deep well, so I'm not even going to go all the way down. Down to where this going up to infinity. And so we are going to model these electrons in a copper block or an aluminum block as being trapped in a well that's of the order of the size of the dimensions of the block. So this is just dimensions L. And we're going to use this again. So one idea I'm just pointing out to you is that the particle and box theory is going to be very important when we talk about conductors and semiconductors. There's an aspect of nuclear physics which is where this type of square well potential is very important. It turns out that if I consider, for example, a neutron and a proton that are in proximity with each other. By the way, this forms a nucleus, and we call this the deuteron. Some of you may be familiar with deuterium as heavy water. You've heard of deuterium as heavy water. There's water that consists of, this is a form of hydrogen, by the way. So hydrogen, H1, is a proton, plus an electron. A variation of hydrogen, I would call H2, and this would be equal to a proton plus a neutron plus an electron, obviously, right? So the whole modeling of what we call the strong force, so the strong nuclear, or also called the nuclear force, is a short-range force, a very strong short-range force. And what that means is that the attraction between nucleons, we know, for example, that if I have any particular atom, let's take, for example, carbon-12, right? Carbon-12. If I take carbon-12, there are going to be 6 protons, there's going to be 6 neutrons, and there's going to be 6 electrons, right? We can look on the periodic table, and as you go across the periodic table, you go from hydrogen to helium to lithium and beryllium and so forth. So this short-range nuclear force is described by a potential well, a potential barrier, and one of the ways in which it is described is now we'll take this out and talk about, we'll talk about 2 nucleons that are formed together within this potential well. Now let's talk a little bit more about this potential function. Right? Remember we said that the force on an object is equal to the negative derivative du by dx of the force with respect to x. So the slope of this function, if I were to approximate this by a more gradual function, it looks something like this, right? Then what I would see is that the slope of this function is positive, and therefore let me see if the force is holding the particles radially inward from the edges of the box, and this is a positive slope, and therefore minus the negative sign times the slope is in the direction which is negative, which is this way. This one is a negative slope, so the force is in the positive direction, and the force holding the particles together is at the boundaries of the box, right? So we can think of a neutron and a proton as bouncing around inside this potential well, and they are bound together with some force holding them together. Now, it turns out that for the case of the deuteron, this potential energy level is fairly high. It is 35 million electron volts. It's a unit of potential relative to this one, which we would call 0. Right? And the bound state energies for the neutron and proton, which are tied together by the nuclear force, occurs at an energy level of about 32.7 electron volts. Or to say another way, there's a potential difference. The binding energy that's holding these together is the difference between the energy at this level and the potential at the outside of the box or the well, and the energy of, this should be million electron volts, and the energy of the ground state for the deuterium. So in this particular, the deuteron, I'm sorry, for the deuteron. So in this particular case, this tells us that the binding energy is equal to 35 minus 32, this should be 33, no? Yeah, 32. Minus 32.7, which is equal to 2.3 million electron volts, right? So this is the binding energy, or the energy it takes to knock one of these protons up and not one of these, but one of these nucleons out of the vicinity of the other one and separate them so that they are free to separate. And I have to supply a certain amount of energy in to break them apart. Right? So without going into details, experiments have been done to verify that this is the binding energy holding between the proton and the neutron. That's how much energy has to be supplied to break the neutron away from the proton. We talked about that last time. The distance from the energy level to the top of the potential barrier is the binding energy. The difference between the energy level and the potential in that region is called the kinetic energy. Okay? So this is a simplified picture of an atom, of atoms being held together. Now, it turns out that this distance L for a nuclear binding of a proton and neutron is a very, very small distance. It's of the order of 2 times 10 to the minus 15 meters. Okay? So, in other words, once the separation distance between two nuclear particles, and by the way, we have a name for proton and neutron. In general, if we refer to either one, a nucleon can refer to a proton or a neutron. So when I refer to nucleon, I'm referring to either one of these. Right? And in this particular case, then, these, as we said, are bound together. But once they get stretched away at a distance which is very, very large by the input of energy into the system, then they can be separated. And that is the binding energy. So I have to supply about 2.3 million electron volts, which could be in the form of an electron, something coming in and hitting the atom. Okay, something coming in hitting the atom is what is causing the breakup of. So I send in a projectile, and the projectile could be a proton, it could be another neutron, it could be an electron, right? But it's got to have an energy of the kinetic. If the kinetic energy is equal to or greater than or equal to 2.3 million electron volts, then that will be sufficient to break apart this two-particle bound system. Right? Now, it turns out that the size of protons and neutrons has been measured. And the size of a proton is, in fact, we can write that the radius of a proton is approximately equal to 10 to the minus 15 meters. And which is also approximately equal to the radius of the neutron. Now, if the maximum separation that these two particles can have is only 2 times 10 to the minus 15, and their radius is 1 times 10 to the minus 15, then they must be very close together at all times. They're almost touching. Okay? And if you see the picture of an atom, like in chapter 42 of a nucleus, you'll see the protons and neutrons are tightly packed. And the idea is that they're just illustrating the fact that the size of a nucleus, or the volume of a nucleus, so if I were to take, let's say, 4/3 pi r cubed for a nucleus, this would be equal to A times the volume of a single nucleon, right, which is a proton or neutron. So A, by the way, is equal to the atomic number, or the atomic weight, I'm sorry, this is called the atomic weight, which is equal to the number of neutrons plus the number of protons, plus the number of protons. So if I take the total number of neutrons and plus the number of protons, I get the atomic weight A, and if I multiply that by the volume, the 4/3 pi r cubed of a proton, let's say, then I then find that the radius of a nucleus is approximately equal to the cube root. Yes, I could draw it that way. Yeah, I can do the cube root of A times the radius of the proton. So this is called the tight packed model of a nucleus. And we found that because of measurements that are done independently on the size of the proton and the size of the neutron and the distance over which the forces appear to be exhibiting a significant amount of force, then we can then come up with how to measure the size of a nucleus. We just take multiply the proton radius by the cube root of the number of nucleons. And so this would be equal to the number of nucleons, right? Okay, now we're going to find out when we go into chapter 42 that the size of a, that the orbital radius of an electron going around a hydrogen atom is approximately equal to 0.05. This is R of the electron is equal to 0.05 nanometers. Okay? Now, 0.05 nanometers is 100,000 times or 10,000 times bigger than this number, 2 times 10 to the minus 15. So the electron is actually at a very large distance from the nuclear volume. Right? And that's another picture you always see of atoms, right? Electrons are always traveling at distances that are very, very large compared to the size of the nucleus, which is your textbook, your third grade picture of the atom is actually based on this whole idea. Okay, so that's an example. So there are real examples in nature where the nuclear force plays a very, 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 very important role, and they can be modeled with this sort of a potential function. Right? Now, sometimes what you will see, instead of the potential being drawn this way, where it goes from U0 down to 0 and back up again, I can also draw a potential function another way, and we'll see this a lot in particularly in the electric force of the electron in going around the nucleus. That what I can do, instead of placing the top of the potential at a very high number and the potential where the particles are likely to be found at 0, I can equally well draw the potential function as something that starts at 0 and goes negative and comes back up in this one. So this one I can also, this case, this would be minus u0, and this would be 0. So what I've done now is I have subtracted u0 from the original potential well problem, and I get one that looks like this, and the physics is exactly the same. So in this particular model, or this particular case, if I were doing nuclear energy, this would be minus 35 million electron volts. And this one right here would be at 2.23, or 2.3, I'm sorry, would be at 2.3 million electron volts, right? And this would be the energy level E1 of the particle, or I should say it is at negative 2.3 MeV, and the bottom of the potential well is at minus 35. They are equivalent. You can, anytime it does, you are allowed to change the value of the potential up to any arbitrary constant. And it does not change the physics. The physics is given by the slope of the potential function. So wherever I wrote that down, right here, right? The physics, the force is the derivative, right? So here the force is 0, here it's 0. The only place there is a force is at the edges of the box, right? Because that is where potential is changing. du by dx is not equal to 0 at the edge of the box. It is equal to 0 everywhere else. So I can always change a potential energy function by adding an arbitrary constant. And there's discussion of that back in your chapters 3 or 4 in mechanics from 253. I'm not going to go through that. But you without changing the solutions at all, you can change the potential uniformly by a constant if you add or subtract a constant anywhere. The problem is the same. Right? It's also nice to think of potential energy as equal to 0 as you go out to infinity. That's also another reason we draw it this way, is that there's a more easily understandable and interpretable way of explaining things if potential goes to 0 as distance goes to infinity, such as in electric force. When the distance between two charges gets stretched to infinity, the force goes to 0, but the potential energy also goes to 0. It's just a convenient way it's a convenient reference, right? Okay, so enough about bound problems. Okay, so now, are there any questions so far? Anybody have any questions on this? Okay, so now we're going to talk about tunneling, and a little bit about what that entails. Okay, so let's consider first the classical system. We talked about this in relation to the finite well. Remember we talked about the idea that, let's say I have a bicycle or a ball rolling on a hill, and it goes up and it gets up to the top of the hill is up here, and the ball has a certain amount of kinetic energy when it's rolling towards the hill, and it has a certain potential energy, mgh, which is the potential energy to reach that is acquired as a particle gets raised to a higher. And the conservation of energy says that, assuming down here we have that u is equal to 0, and over here it's equal to mgh, right? Then that as the kinetic energy decreases going up the hill, the potential energy increases. And so the criteria that the particle can make it up over the top of the hill is that if the kinetic energy down here, which as we said, we know is 1/2 mv squared, right, is greater than mgh, then the ball passes over the hill. Right? That's the for in the absence of friction, that the ball can make it passes not over the hill, but passes to the top of the hill. Now, this we said was this is the general case. For the cases that we have been considering in the potential well problem, we've had cases where 1/2 mv squared, which is the energy of the quantized energy levels, is less than U0, and in that case, we find that the particle cannot make it to the top of the hill. Reach top of hill. Cannot reach the top of the hill. Classically. Or in other words, from energy conservation. Energy conservation, right? But we know in a quantum system that, in fact, it is possible for the particle to be up here, even though the kinetic energy is less than the potential energy, which in this case we'll call U0. So 1/2 mv squared, and we gave an example of that last time. So we'll do a similar example today, only I'm going to make it a little different. So we chose a height, barrier height of 1 meter, and we chose the mass of the particle equal to 1 kilogram. And then we get that from this, that U0 is equal to 9.8 joules. Right? So the height of the barrier is 9.8 joules. What is the kinetic energy that it's starting from? Well, let's suppose that the velocity at the bottom of the hill is equal to 4 meters per second. Right? Then 1/2 mv squared will be equal to 8 joules. Okay. And we would typically say that 8 joules is less than 9.8. It cannot make it to the top of the hill. But quantum mechanically it does. In fact, it actually does make it to the top of the hill. But it can only stay there for a certain amount of time. But what if instead of having a hill that stays, we will say, flat up here, it actually comes back down here? Now, we would argue that if there's a finite probability that it can violate energy conservation and make it to the top, then a little bit further out, it can certainly be there because now it's got more and more kinetic energy. The potential barrier is less and less. Once it reaches out here, it will continue to go all the way through. The velocity will continue to increase. So this process is called tunneling. And the reason it's called tunneling is because if the kinetic energy is too small to allow the particle to make it through the barrier, then it's as if we have actually drawn a tunnel through the hill. And it is as if what happened was that when it got up to a potential energy of 8 joules, which means that all of the kinetic energy has been lost, it can just make it over here and it's got just enough energy to get across and come down the other side. Right? It's as if there's a tunnel that the electron can go through if tunneling, and we call this an analogy, meaning that scenario where energy is conserved. Energy is conserved, and by energy being the way we would describe that, if energy is conserved, is that we would say that the particle has found a path such that it never violates energy conservation, but it makes it across through here, and once it gets through here, it comes down the other side. So the idea of tunneling means that it's a classical description of a quantum mechanical event. Quantum mechanically, we know, because the wave function has solutions in classically forbidden regions, that the particle can be up here, and then, the probability decays exponentially as you go further and further away from the barrier. But if the barrier falls back down, as this does in the classical hill example, then if the probability is non-zero when it reaches the peak, the point right here, it certainly has been able to physically materialize on the other side. Okay? So if there's the tunneling effect is such that there's a probability that it was able to violate energy conservation enough to make it to the other side of the hill, then it can certainly make it beyond that, because now the potential energy is helping it gain speed rather than fighting its energy speed. And so if there was in fact a finite probability of it making here, it's certainly going to be here, 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 and here. And furthermore, it's not going to have to rush back to the other side as it did before. Okay? So that's the idea of tunneling. So stop for questions. Tunneling. See if you have any questions about tunneling. Yeah.
Would this only happen with like atomic particles, or does it actually happen with
Only atomic particles. Yeah, you can apply the same equation, but it turns out that if you use the mass of a ping pong ball, or you use the mass of a speck of dust, it's way too big to give. I mean, the probability is non-zero, but it's 10 to the minus 70. Right? Which means you would have to wait 1,000 lifetimes in the universe before such an event would actually occur. So the probability becomes so astronomically small, the answer is no. Even though there's a finite quantum probability event, it's never going to happen in 1,000 million lifetimes in the universe. Right? The probability is just too small. Right? So if it's effectively zero. But the same event, I mean, the same thing can occur. I can, for example, in this case right here, notice that the energy violation that's required the energy violation of energy conservation that's required to make it to the top means that delta E has to be equal to 9.8 minus 8.0 equals 1.8 joules, right? How long would that particle actually be able to stay up there and be observed? Well, the uncertainty principle says that the amount of time that it could actually be up there would be given by h bar, and this is approximately 10 to the minus 34 joule seconds is the value of h bar divided by 1.8 joules, and the amount of time that it could spend up there is 10 to the minus 34 seconds. And one can measure 10 to the minus 34 seconds. Right? So, furthermore, the particle would have to be going faster than the speed of light, which violates Einstein's principle, and it would not be able to get to the top and get back fast enough. So, yeah, I mean, the idea is that once you start applying these to large macroscopic objects, the probability is so small, we just say it's not happening. When does it become? When does it happen? Well, when we have particles which have masses. The largest mass we typically deal with might be the mass of a proton, for example. That's 938 MeV, which is MeV over c squared, I should say, right? Or when we have, and the energy, the kinetic energies are also measured of the order of 100 or 1,000 MeVs, right? Which is already, by the way, 10 to the minus 13 joules, right? That's a very, very small quantity of energy. Then, in these cases, you can begin to see quantum effects. But the energies have to be extremely small, such as with protons, electrons, and neutrons. And the masses have to be extremely small, such as with protons, electrons, and neutrons. Right? Because it's all in relation to this quantity h. And h is such a small number that in most cases we can't see the effect for macroscopic objects. Right? But the entire electronics industry is based on quantum theory. And as small and unlikely as it is for objects of macroscopic size, understanding how electrons move in circuits is dictated by quantum behavior of the electrons. And all of, you know, I think it was the physicist Leon Lederman that said that 30% of GDP is based on the theory of the gross national product in the United States is based on quantum mechanics, quantum theory and thermodynamics, but basically any modern physics concepts contribute, have generated the economy of 30% of the gross national product. So small particles can be important. They lead to very important macroscopic devices. Okay, so in the last half hour or so that we have, we're going to talk about the how to describe the tunneling properties of a particle, and so start that right now. Almost right now. Okay, so, nope, I want one more page before I start. If I can. Got it. Okay, so how do we describe tunneling? Okay, so the basic idea of tunneling is that, correct color pencils here. We are now going to deal with a barrier that looks like the inversion of the potential well. We want to invert this potential barrier so that the potential of U is a constant here, it goes high and then low again. That's the whole idea of a potential barrier, just like a particle climbing to the top of the hill. So, or losing energy as it goes to the top of the hill. So I draw my energy diagram, and the energy diagram is given by the potential. So in this case, I'm going to take a potential which is equal 0. It goes up to some value called U0, comes back down again, right? So this is U0. And now what I'm going to do is to take a particle that has a total energy E, which is less than the potential barrier, such as we did with the ball going up the top of the hill. And I have a total energy E coming in here. And this is the energy of the particle. And this is 1/2 mv squared. Right? And quantum mechanically, I describe this particle as being a wave. And now I'm going to assume that there's actually a stream of particles. Right? There's a stream of particles coming in here one at a time. But it's a constant stream, and that is hitting this barrier. Now, if this was a classical system, then when it hits this barrier, all of the particles get reflected back. It's like, you know, particles hitting a brick wall. When they hit the wall, they bounce back. So I will have what's called an incident beam or wave of particles. So I'll have particles of momentum P1 that are, which is equal to mv, right? Or mv1. And I will have particles reflected coming back that have energy minus or same energy 1/2 mv squared, but the momentum P1 is in the minus direction and it's coming back this way. Okay? So I've got a particle that is incident on the wall and it gets reflected. Now I'm going to describe the solution over here to this particle. So this particle now has a wave function, and I'm going to describe that with a. First of all, I'm going to label these three regions as we've done before: 1, 2, and 3. Right? And Now what I'm going to do is say there's an amplitude, a wave function psi in the region 1 of space, and that's given by some amplitude times e to the I p1x over h bar, and there's a reflected wave, which is e to the minus I p1x over h bar. Notice that I'm leaving out the time dependence because there's no time dependence. It's a steady stream of particles coming in, therefore there's a steady stream that's getting reflected, but we now know because of the wave property of hitting a barrier that there's an exponential decay of the particle probability until it reaches the other side, and then it begins to oscillate with the wave, the de Broglie wave begins to oscillate with a smaller amplitude. Okay? So this is the region of exponential decay, which is what we found in the finite well back here, right? This is the region where the probability of finding it past the barrier decreases exponentially. And the same thing is here, only now, because it hasn't gone to 0, it actually reaches the other side and it begins to oscillate again. Okay? Okay, so now we need coefficients. Now, by the way, the Schrodinger equation is the same as before. Nothing's really changed here, so I can do a minus h bar squared over 2m times the second derivative of psi with respect to x, right? Plus u of x times psi equals E times psi. E is the total energy, or I can write this. There's a couple. Yeah. So I can also write this as the second derivative of x of psi with respect to x plus. Let's do it one more. Let's say, for example, we are in the forbidden region where u is greater than e, then this becomes minus u0 minus e times 2m divided by h bar squared times psi is equal to 0. Okay? So we've had this before, right? This is simply the constant that we call g in the forbidden region, and this is going to be the solution in region 2 for psi 2 of x, right? And so psi 2 of x is going to have an exponentially decaying function, which is e to the minus gx, right? And out here in region 3, I'm going to have a solution, which is the transmitted wave. So we have 3 waves that are present in this phenomenon. This is the transmitted wave. So psi 3 of x is the transmitted wave. It actually is the sum of the particles actually make it through the barrier. Some of the particles get reflected at the barrier and they get coming back the other direction. And this right here will be the reflected wave. And this right here will be the incident wave. Right? This is reflected, this is incident, this is the transmitted wave. Okay? Everybody see that? There are 3 waves involved here. You know, electron hits the barrier, it's either going to be transmitted or reflected. That's the basic idea. One second. Okay, so we're going to make this nomenclature a little bit different, but it's going to reflect the same sort of things as we had before. But now I'm going to write that psi 2 of x in this region is e to the minus p2 over h bar times x. So it's an exponential decay, and p2 is equal to the square root of 2m times u minus e. Right? Where, or u0 minus u0 minus e. Right? So this is the same statement as this, only I just redefined g by including, in this case, g is equal to p2 over h bar. That's probably the best way of saying it, right? Okay, so that's one thing. So we have solutions, incident wave. This is in the forbidden region, and psi 3 is in the transmitted region, right? And what we are now doing is saying that there are coefficients which we will add together, that if this is a solution of the equation and this is a solution of the equation, then any linear combination, and so forgive my order at which I create constants, but for reasons of doing this earlier, the coefficient in front of the incident wave is d, the coefficient in front of the reflected wave is e, the coefficient in front of the intermediate wave is c, so I'll put a c right here, and psi 3 of x is also a transmitted wave, but it has lower amplitude, so it's going to have a different coefficient, which is, we'll call it a times e to the I p1 x over h bar. Right? So I have, this is the incident wave, this is the transmitted wave, and this is what gets through. And what this is the wave that connects the incident wave to the transmitted wave. Right? This is the exponential decay part, which is right here. This is psi 2, such as what we had for the potential barrier. Okay. All right. So what else do I want to do? All right. So now, what are we looking for? Well, what we want to know is what is the probability? What is probability that an electron with energy E less than U0 is transmitted through the barrier? Through the barrier, okay? We know that for the classical system, the answer is, the probability is what? What?
Zero.
Zero, right. Classical system, the energy is, kinetic energy is less than the potential energy, can't make it through, nothing comes out. Right? For a quantum system now, we're treating it as a wave, and because of the wave now has a penetration into the classically forbidden region, when it comes out the other side, it's still going to, its probability doesn't go to zero, right? Because once it makes it to this side, it's made it on out to infinity, right? Plus, whatever potential energy it lost going up the barrier, it gains coming down the barrier. So the momentum is the same on this side as it is on this side. So notice I have momentum P1 for the momentum of the transmitted wave. It's the same as the momentum P1 of the incident wave. What's different is how many get through. Right? So it might be that for every 100 electrons that come in here, only one of them gets through, and that's reflected in this quantity A, this amplitude. Right? So how do we calculate this probability from a point of view of the quantum system? Well, the quantum system, we'd say that the probability that it makes it through is equal to psi 3 squared. Psi 3 squared is equal to the probability of transmission. But I also have to know something about the probability that the particle reached the wall or reached the barrier in the first place. So psi 1 squared is the probability of electron reaches the wall. And so what I'm going to write is that the transmission probability is equal to the ratio of psi 3 squared divided by the magnitude of psi 1 squared. So this is the probability that it makes it to the, in region 3. So this is equal to the probability in region 3, electron in region 3, divided by the probability that the electron was in region 1. Right? It's the ratio of the probability. So the way we describe that numerically is that the amplitude of the de Broglie wave is smaller here than it is here. And the reason is quite simple, that the amplitude is very high, reaching this barrier. It decays off exponentially, and then the amplitude is small. So this ratio of this amplitude to this amplitude is given, it gives us exactly the value which we call the transmission. Okay, so let's evaluate that. First of all, what is the amplitude squared of psi 3? Well, it turns out that the amplitude psi 3 squared is equal to the amplitude A squared times the amplitude of, or times the amplitude or the absolute value of the exponential, which is 1. Right? And in the region of psi 1, this is the incident wave, psi 1 of x, and now I'm only considering the incident part is equal to d times e to the I p1x over h bar. And the absolute value of psi 1 is equal to d squared times the absolute value of e to the ipx over h bar. And from the notes that I handed out to you a week or so ago, this value is equal to 1. Right? This part is equal to 1. So now the transmission is equal to what we would call the psi 3 squared, which is in this case is a squared divided by d squared, which in simple terms is basically a is the amplitude of this wave. So a is the amplitude of this wave, and d is the amplitude of this wave. Right? So d is the amplitude of this wave, a is the amplitude of this wave, and the ratio of a over d squared is the amount that gets transmitted. Right? So it's a wave technique of calculating this. Now, in the book, what they tell you is this has already been done, and the answer is it's e to the minus gamma, and gamma is equal to the square root of, it's actually, I think it's 2 times the square root of 2 mu minus e divided by h bar times the width of the barrier, which in their notation is w. I'm going to call it a. A is the nomenclature that I'm using. The book's notation, the width of the barrier is equal to w. Okay? And I believe that is basically all that they tell you, is that this is the answer. And if you want to know what is the probability that the particle makes it through a classically forbidden region, then into, or can penetrate through to the other side of a barrier, this is the equation you use. And what I'm going to try to do is try to explain why that equation is true. I'll make sure that I didn't leave anything out. Yeah, that's right. Yeah, yeah. And you can verify that my equation is consistent with the one in the book when you go about and try to work some of these problems. Okay, so how do we calculate the ratio of A over D quantity squared? How do we get this? Number one, this is not the correct answer. It's an approximate answer. However, for some cases, it can be off by a factor of 50. The one that I was looking at worked out in the book, so it's you know, approximate equal here, right, like this, and it's not exactly the exact one. Okay, so how do we do that? Well, first what we're going to do is we're going to use the boundary condition. The wave function has to be continuous from here to here. So this is going to give a relationship between the amplitude D and the amplitude in the forbidden region, which is an amplitude of C. Probably should use, maybe try to use a different color so it becomes a little more transparent. But this has amplitude D. This has a coefficient C. And over here I have the coefficient A, right? So if I can express D in terms of C and C in terms of A, then I can express D in terms of A. Right? And that's the path we're going to use. Then I can take the ratio of A divided by D, and that will give me the probability that the particle can make it through the barrier, the classically forbidden barrier, and actually be observed on the other side. And this is in fact actually based on observations. These are actually experiments that you can do that have been done to verify that this effect, which we call tunneling, is real. That particles really do show up on the other side of classically forbidden barriers where, because of conservation of energy, they would not be allowed to occur. Okay. So, is that a cell phone up in the back corner? Yeah, cell phone's off, please. Thank you. And I'm sorry, computers closed too. Laptops all closed. Okay, so now then what we want to do is to find out how to use these boundary conditions. Okay, so the boundary condition is that at x equals a, which is the right barrier right here, that we know that the wave function psi 2 at A has to be equal to the wave function psi 3 at A. And so putting values in here, I get that this says that C times e to the minus p2 times A over h bar is equal to capital A times e to the I p1 A over h bar. Okay? And furthermore, the derivative, is everyone familiar with the derivative notation prime? Okay, so this is my new derivative notation, psi prime. Psi prime 2 evaluated at A is equal to psi 3, the derivative of psi, of psi 3 evaluated at A. And so I get another equation that says that minus C times P2 times e to the minus P2 times A over h bar is equal to A times IP1 times e to the IP1 A over h bar. Right? So that is the condition that the first derivative is continuous across the boundary at x equals A. Right? So that gives me a second equation. And I can solve these two for C. I can solve this equation for these two for C. And I can get that that C is equal to A over 2 times 1 minus IP1 divided by P2 times e to the I P1, IP1 plus P2 times A divided by h bar. Okay. And now I can do the same thing for the wave function has to be continuous across the boundary at x equals 0. So at x equals 0, I have the condition that psi 1 of 0 must be equal to psi 2 of 0. The wave function must be continuous. And I then get that d plus e is equal to C, because I evaluated the exponentials at x equals 0. Then I do a fourth equation. So this is equation number. We'll call this equation number 4, or let's call this equation number 4. This is equation 3, and this is equation 1, and this is equation 2. Right? So I have equation 1, 2, 3, and 4. And now I also have to have an equation for the derivative. The condition is that the derivative of psi 1 with respect to x evaluated at x equals 0 must be equal to the derivative of psi 2 evaluated at 0. And I get a new equation that says that IP1 times D minus IP1 times E is equal to minus P2 times C. And this is equation 5. Okay. 4 plus 5, so in 4 plus 5, I take D and E. I want to solve for either D and E in terms of C. So I can look at this as 2 equations and 2 unknowns. I can solve for D and E, but I'm only interested in D. D is the one that governs the transmission of the wave. So I'm going to solve 2 equations and 2 unknowns, not just for D and E, but not for both D and E, but just for D, and I get that D is equal to C over 2 times 1 plus I times P2 divided by P1. Okay, now we're almost there. This is equation number 6. Equation 6, right? 1, 2, 3, 4, 5, 6. Now, all I need to do is put in, put in the value of, how do I want to say this? Best way to, take this value of C and put it in over here. Then I have D as a function of A. And you get that D is equal to A over 4 times 1 plus IP2 divided by P1. At very least, you get to understand that we're using boundary conditions over and over again, and that a wave has to be continuous across a boundary. And so does its first derivative. And this allows us to find solutions that we otherwise would not be able to do. It's the only way in which we can actually find solutions to equations. E to the I P1 A over H bar times E to the P2 A over H bar. Okay, notice I have D and I have A. What I really need is the ratio. I need the ratio of A squared divided by D squared. Right? So I can do that. I can do A to put D, divide this equation by D. I get A over D, then multiply by the inverse of the rest of that stuff, and then what I get is that I can then solve this thing for A over D, right? And probably the best way to do this is this way. Let's first of all square everything that's in here. So I take the magnitude squared is equal to A squared divided by 16. The amplitude of the magnitude squared of a complex number is the real part squared plus the imaginary part squared. So this is 1 plus P2 over P1, quantity squared. And it would be like this, right? And I want to, that's what I have. Okay, now, same thing goes for here. This becomes 1 plus P1 divided by P2, quantity squared. Okay. And the square of this term is 1. This is an exponential. So the magnitude of this complex quantity is equal to 1 because it has a cosine term that's real, a sine term that's imaginary. Sine squared plus cosine squared is 1. That's the real and imaginary part of this exponential. So this whole thing is 1, and this becomes e to the 2p2a over h bar squared. Okay. Now I just need to resolve this for a squared over d squared. A squared over d squared. So a squared over d squared becomes 16 times 1 plus p2 over p1 quantity squared times 1 plus p1 over p2 quantity squared, right? Times the exponential, which in the terms that you're given in the book is e to the minus gamma, right? And my value of gamma is where gamma is equal to this exponential. Or it's a square root of that exponential. So this is equal to P2 times A over H bar. And this is then equal to, e to the minus gamma. My mistake. This is e to the minus 2. So equating these in terms of their exponents, it's gamma is equal to 2 times the square root of 2m e 2mu minus e times a divided by h bar. Right? And that is the value given in the book. In the book, what you're given is this term. They're telling you that this is the correct answer. Right? What I've just derived for you is that that's only part of the answer. The rest of it is this term. And by the way, P1 is just the momentum, right? 2m times e, right? P2 is the same structure, but it's 2m times u minus e, right? So P1 and P2 are constants. E is the total, is the instant energy. U is the height of the barrier. This is the probability that a particle makes it through and tunnels through the other side, right? So basically, you could, if you are asked to solve a problem in the book, I'm not sure I gave you one, I'm not sure I did for this assignment, obviously you have to use the value that they give you right here, right? Now, I'm not going to ask you something this complicated on test, but I might ask you how I would go about solving it. You know, like I might ask you a question about the way that transmission is calculated is based on what principles? I might ask you something like that. But this is the term that's given to you in the book. Obviously, it's not exactly the correct expression. And I thought that it wasn't that hard to derive. I mean, to me, it wasn't that hard to derive. But it does emphasize that the way you solve problems in quantum is that you have, these are all called boundary conditions. And you do the same thing if it's for the hydrogen atom, if it's for a particle in a box. Any wave equation you have has to have boundary conditions in order for you to be able to solve for the wave pattern. And part of that is solving for these, in this case, these coefficients. The boundary conditions are that the wave function has to be continuous across any given point. The derivative of the wave function has to be continuous. And of course, the same has to be true at the other boundaries as well. So, this is how you calculate a transmission through a classically forbidden region. Right? And I think you now have all the equations you need, probably calculated. And I think that's probably, any questions you want to ask on this? Yes?
So on the magnitude of d squared, the first set of parentheses where it's 1 plus p squared over p, or p2 over p1 squared?
Yes.
Wouldn't that be a minus thing as when you square the I it'll be a -1?
No, because regardless of whether it is, if it's A plus BI or it's A minus BI, the magnitude of this is the same. They're equal.
Okay.
Okay? It's the length of the vector of the real and you can plot the real and imaginary part of a quantity, let's say psi, on the axis. And so this is the real part, this is the imaginary part, B, and you're finding the length between them. Right? And so even if it was minus BI, the magnitude of a complex number, this magnitude is the same as this magnitude. So it becomes positive. I'm sure you'll have examples in your classes later on using complex numbers. So this is, even if this is the first time, it's not the last time. I don't think you'll end up seeing it.